Welcome to the Explainer. All right, today we're diving into what is arguably humanity's most complex logistical puzzle ever conceived, sending actual human beings to the planet Mars. Now, exploring Mars with a human crew, it's widely viewed as the absolute culmination of planetary exploration. But getting there and, well, more importantly, surviving and getting back, that requires solving engineering and chemical problems on a scale we've just never faced before. So let me ask you a question right off the bat, just to set the stage here. How do you pack for a 3-year camping trip to a freezing desert that's up to 140 million miles away? Especially when there are absolutely zero gas stations or grocery stores anywhere along the way. I mean, think about the sheer impossibility of carrying literally everything you need to survive. Every single drop of water, every breath of air, every ounce of fuel to get you back home. It is a staggering challenge, and it's going to require an entirely new way of thinking about spaceflight. Okay, let's dive into this. Here is our roadmap for today. We'll start with NASA's master plan, then we'll look at the timing of the trip, move on to the weight problem, and finish up with living off Martian land. Let's hit Section 1, NASA's master plan, basically building the bridge to another planet. So what we're looking at here is NASA's Moon to Mars architecture document. This is the comprehensive blueprint, the literal roadmap for our future in space. And it's not just some static, one-and-done mission manifest. Actually, scratch that. It's more like a living, highly adaptable framework. It's designed specifically to break down these massive, mind-boggling Moon to Mars objectives into actual, implementable capabilities. And there's this fascinating foundational design philosophy driving the whole plan. It goes like this: architect from the right, execute from the left. Now, I know that sounds a bit like a riddle, but the logic is absolutely brilliant. It basically means you start with your ultimate long-term goals on the far right side of a timeline, like getting human footprints on Mars, and you work backward to figure out exactly what capabilities you're going to need. Then you execute from the left, starting right now in the present day, building out those capabilities step by step. Let's move to and see how this actually builds in practice. This philosophy unfolds across 4 very specific mission segments. Step 1 is human lunar return. That's establishing our initial capabilities. Step 2 expands that into foundational exploration. Step 3 is sustained lunar evolution. And only after mastering all of those do we finally reach Step 4, humans to Mars. You see, the moon serves as this vital incremental proving ground. We have to learn how to live and operate in deep space just a few days from Earth before we ever commit to a journey that takes years. Moving right along to Section 2, the timing of the trip and orbital mechanics. Here's the thing about Mars. Launch windows only open up roughly every 26 months. Because Mars has a highly elliptical orbit compared to Earth's, the distance between our 2 planets varies wildly. So unlike the moon, we are locked into a super rigid launch schedule. We can't just pack up and leave whenever we want to. We literally have to wait over 2 years for the planets to align perfectly to make the trip mathematically possible. And this brilliantly illustrates the big dilemma. Once that launch window finally opens, mission planners face 2 primary trajectory options. We've got the conjunction mission, which is your long-stay profile, versus the opposition mission, which is the short-stay profile. And guys, these 2 options present a massive, massive contrast in how a Mars mission would actually look and feel for the crew. The contrast here is just staggering. In a conjunction mission, astronauts spend a massive 558 days on the Martian surface. That makes for a total round trip of just over 1,000 days. But in an opposition mission, the total trip is much shorter, around 560 days, but they only get about 40 days on the surface. That is a brutal trade-off. Do you minimize the heavy radiation exposure and that terrible physiological toll of weightlessness by taking the short option? Or do you maximize the scientific return on your multi-billion-dollar investment by staying on the surface for over a year and a half? Which brings us to Section 3, the weight problem, or the mass penalty of spaceflight. Let's bring it back to that ultimate camping trip analogy for a second. If you're going to stay on Mars for 500 days, or hey, even just those 40 days, you simply cannot pack your own water, air, or gas for the drive home. Bringing all our return supplies all the way from Earth, it's completely infeasible. The rocket would be so incredibly heavy, it wouldn't even be able to lift off the launch pad. And why is that? It all comes down to a concept called the gear ratio. And the math here is pretty staggering, 8 to 10. That means for every 1 unit of mass you want to land on the Martian surface, you need 8 to 10 units of mass sitting in low Earth orbit just to get it there. To put that into perspective, going to the moon has a gear ratio of only about 2.5. So trying to deliver mass to Mars is mathematically punishing. And that brings us to this incredibly heavy number, 30 tons. Get this. It takes about 30 tons of oxygen propellant just to launch a vehicle off the surface of Mars to head back home. If we had to actually bring that 30 tons of fuel with us all the way from Earth, multiply that by our 8 to 10 gear ratio, we're talking about needing up to 300 tons of mass in Earth orbit just to deliver the return gas. There's no way. That completely breaks the mission. So, how do we fix it? That's Section 4, living off Martian land through microscale chemistry. So the crucial point is this. To get around that impossible math, we rely on ISRU, or In-Situ Resource Utilization. Now, I know it sounds like a clunky technical acronym, but trust me, it is the magical key to deep space survival. ISRU basically means processing local materials on another planet to create necessary life support and propellant. Simply put, we don't bring the fuel with us, we make the fuel when we get there. And luckily for us, Mars has abundant local resources, or feedstocks, that our astronauts will be able to harvest. We've got carbon dioxide straight from the Martian atmosphere, we've got embedded ice up at the high latitudes, and hydrated minerals right there in the regolith, the Martian dirt. Now, for those very first missions, processing the atmosphere is by far the simplest first step. We don't even have to send autonomous robots to go out and dig. We literally just pull the resources right out of the thin Martian air. This right here, this is where the magic happens. Through some absolutely incredible chemical engineering, we can take those local resources and transform them. Check this out. By using the Sabatier reaction, we can combine Martian carbon dioxide and hydrogen to output methane for rocket fuel. And through electrolysis, we separate water to get pure breathable oxygen. We are literally creating our ride home and the air we breathe out of the freezing Martian environment. It is absolutely mind-blowing. Now, what's really interesting about this is that it's not just science fiction. We've actually already done it. A device called the MOXIE experiment recently traveled to Mars aboard the NASA Perseverance rover, and MOXIE was a highly successful prototype. It used solid oxide electrolysis to produce actual breathable oxygen right from the carbon dioxide in the Martian atmosphere. It was literally the very first experimental extraction of a natural resource from another planet for human use. The proof of concept is already sitting up there on the red planet for sure. So, we've covered a lot today in this explainer. We looked at the macro blueprint of NASA's architecture, those punishing orbital mechanics, the terrifying weight constraints, and the incredible chemistry that actually makes survival possible. But ultimately, when humanity finally steps foot on that distant world, mission planners and the astronauts themselves are going to face a monumental choice. Knowing the immense physiological risks and the massive scientific rewards, would you choose a short 40-day dash on the surface? Or would you commit to a massive 500-day stay to make history on Mars? Think about that and keep exploring.